We're now looking at expectation functions. Random processes or random variables can have expected values. And so one of the key differences between maybe the expected value you've run across before and what we're going to see now is that with a random process, each index may have a different mean and variance. And so what does this mean? No pun intended. That means that averages, in the sense of finding an expectation, should be taken across realizations or ensembles and not across time. Okay, so at every point in time we may have a different average, and we saw something like that last time when we looked at this beep from, say, a truck backing up. Every time we listen to it, it's the same beep, but it'll be a little bit different. If we were to average all the values across time, we would get 0. I suppose that would be useful in some cases, but not if we're trying to figure out what the underlying beep is like. However, if we listened a lot of times, lined them all up, and averaged those together across realizations, then we would get kind of the average beep. That's what we're going for with these expectation functions. So, the mean of x of n, and sometimes we use a mu instead of the m, so I might go back and forth between that without thinking, is just equal to the integral xp xn x comma n dx. So we're not integrating across n. We keep n the same for the whole thing. So this is our expected value or mean. We can likewise take the expected value of a function of a random variable. Why would we do this? Variety of reasons. But essentially, there's not much mystery here. We just throw the function in there instead of the random variable itself. So this is the expected value of a function. So why would you want to take, what does the expected value mean? What does this integral really mean? So intuitively what it's saying is I'm going to have some value. It may be a function of a random variable such as the power, and I want to know, what is my average power going to be? Well, the power for any given x is going to be x squared, and the probability of that x being chosen is given by our probability density function. So we multiply that particular x squared, that particular power, times the probability density function at that point to give us the probability of that power showing up, and then we average across the whole space, all possible values that x could take on. So that's the integral. Now we don't have to do any division because actually that's part of the integral, right? The smaller the slice, the more it's multiplied by dx. So dx performs the quote-unquote averaging aspect of it. So in this example, average power would simply be the expected value of xn times xn conjugate. Most x's are real, and so this would then just work out to the expected value of the magnitude of x squared, or x squared if it's real. So we have just the integral of xn squared times the probability density function of xn dx. Okay, so another commonly used statistical value is the variance, and the variance of xn is given as how much. It's essentially the power in the variations from the mean is what variance is going to be. So it's going to be x of n minus mx of n, and in case it's conjugate or complex, we multiply it by its conjugate. If it's real, it's just squared, and we define that as sigma squared of x of n. So I'm going to highlight this and this definition, and then let's go through and look at what happens, a way of simplifying this, and it'll help us see a few properties of expectation. So this is going to be, the variance will be the expected value. We can multiply these out of xn times xn conjugate. It's going to be magnitude xn squared. Okay, so we'll have the magnitude here, and then we'll have minus mxn x star of n minus xn mxn star plus magnitude of mxn squared. Okay, to get any further, we need to go back to the definition of expectation. An expectation is an integral, and the integral of a sum is equal to the sum of the integrals. We can swap the order, and we can do that here. So we can write this as the expected value of xn squared minus the expected value of mx times x star n minus the expected value of xn mxn star plus the expected value of mxn star. Well, that gets us someplace. We've used more ink, so it didn't save us any ink, but maybe it's a little bit simpler. And now we need to look at the expectation of a scalar or constant function. The expectation of a scalar or constant function is Let's do a little aside here. The expectation of A, where A is constant, is equal to the integral over whatever PDF is active at the time, well, since A is not a function of x, it can pull out of the integral, and we get minus infinity to infinity of pxx dx, and that value is equal to 1. So it's just equal to A. So how does that apply here? Well, it doesn't help us with this first value, but with the next one, we can pull out the mx, which is a constant at this point. We've determined what the mean is. The mean might be 7 or whatever it might be. And then we have the expected value of x star minus mxn star times the expected value of xn plus the expected value of a constant squared is just going to be that constant squared. So mxn squared. Finally, this is going to be mxn star, and this will be mxn. So we have each of these values is equal to mxn quantity squared. So we have now the expected value of xn squared minus 2 times the magnitude of mxn squared plus 1 times the magnitude of mxn squared, which just gives us minus mxn squared. So the variance, which we've already come up with a shortcut way of writing, so let's use it. Is exactly equal to that. We can calculate it in either way.